Let's jump right into this explainer of a really fantastic MarkTech post tutorial. Today, we're unpacking something literally every AI engineer and researcher wrestles with, constructing a highly optimized, memory-efficient AI model from scratch. We're going to walk through the exact steps to build a model that doesn't just work, but works incredibly efficiently on your GPU. So here's our game plan for today. We'll start with the transformer memory bottleneck, move into benchmarking speed in memory, cover sequence packing and GQA, unpack ALiBi positional biases, and finally wrap up by actually training a GPT block. All right, part one, the transformer memory bottleneck. Now, we all know transformers are absolute powerhouses, right? They've revolutionized language, vision, biology, you name it. But here is the massive catch. As your sequences get longer, maybe you're parsing whole books or massive code bases, their memory demands scale quadratically. It is a literal exponential explosion. If you double the sequence length, you quadruple the memory needed for the attention mechanism. That means you can't just throw a bigger, more expensive GPU at the problem and expect it to go away. It's a huge wall you hit when scaling context windows. So our core problem today is this: how do we bypass this quadratic bottleneck without sacrificing the model's fundamental capabilities? Enter our hero, xFormers. This is a super practical toolkit designed specifically to build fast, memory-efficient transformer models directly on GPUs. And what's really fascinating here is that it pulls this off without changing the fundamental attention calculation. We aren't doing some sketchy approximation or sparse attention trick. It's exact attention, just engineered brilliantly at the GPU kernel level. By dynamically fusing operations together, it completely avoids writing massive intermediate steps to memory. So our first step is just validating that this highly optimized approach mathematically matches standard naive attention. Moving right along to part two, benchmarking speed and memory. Because let's be real, we can't just take the toolkit's word for it. We need to see the actual numbers. When we benchmark naive causal attention against xFormers attention across progressively longer sequences, the contrast is honestly stark. With the naive approach, as you push that sequence length up, your GPU memory usage just spikes aggressively. It climbs and climbs until you inevitably get that dreaded out-of-memory crash. But with xFormers, you see exactly how it dodges that quadratic memory growth. It keeps the memory footprint totally predictable and manageable, even as those sequences stretch out into thousands of tokens. Just to be super clear on the setup, the tutorial rigorously tests both the forward and backward passes. They measure the raw execution time and closely track peak GPU memory usage, all while applying an implicit lower triangular causal mask, which is totally standard for your GPT-style autoregressive models. By actively tracking execution times and peak memory during these specific passes, we're not just guessing that it's better. We're literally proving the immediate benefit. We're saving massive amounts of memory, speeding up execution, and maintaining absolute mathematical accuracy the entire time. Let's hit part three, sequence packing and GQA. So in the real world, data is messy. You've got variable length sequences. Normally, you just pad the shorter sequences with zeros to force them into a uniform batch size. But padding is basically wasted compute. Your GPU is sitting there doing math on empty space, burning precious bandwidth for literally zero informational gain. Instead, we can just concatenate those variable length sequences directly into one long, continuous sequence, eliminating padding completely. Then we apply what's called a block diagonal mask. This mask acts as a strict boundary, preventing attention from bleeding across different sequences. That way, a document doesn't accidentally attend to a completely unrelated document shoved right next to it. Finally, you recover the individual sequence outputs. It's just a wonderfully efficient way to run packed causal attention for decoder workloads without wasting a single flop. Next up, we implement grouped query attention, or GQA. If you've spent any time with multi-head attention, you know that keeping the key and value states in memory, the infamous KV cache, is a massive bottleneck during inference, especially for long contexts. By allowing multiple query heads to share a much smaller number of key value heads, you drastically reduce the cache memory you need. You still get the nuanced quality of multi-head attention, but with the speed and memory footprint of something way lighter. It's a game changer for inference throughput. Okay, part four, ALiBi positional biases. So we've got our attention running fast, and our sequences are packed tight. Now we need to deal with how the model actually understands the order of tokens. Because remember, standard attention is totally order agnostic. Normally you'd use absolute or rotary positional embeddings here, but for this build, we use ALiBi, attention with linear biases. By constructing a custom ALiBi tensor, we apply a different linear positional penalty to the attention scores of each head. Basically, tokens that are further apart get a larger penalty. We combine this additive bias directly with our causal mask to ensure tokens only look backward at valid previous positions. By doing this, we bypass standard positional embeddings completely. It saves memory, and best of all, ALiBi allows the model to extrapolate to sequence lengths way longer than what it was originally trained on. Finally, Part 5. Training a GPT block. This is where it all comes together, the climax of the build. We're taking all these isolated, highly optimized tools and putting them together on the workbench. We're combining everything into a compact, trainable GPT-style block. We've got our causal xFormers memory-efficient attention acting as the engine. We wrap it up with standard residual connections and layer normalization for stability. And for the feed-forward network, we upgrade to SWI-glue layers. These have pretty much become the industry standard for state-of-the-art models like Llama because they offer significantly better performance and gradient flow than traditional activations. But a blueprint doesn't mean much if the building collapses when you stress test it. So we put this assembled block to work. We train it using automatic mixed precision, which means using lower precision floats where we can to save even more memory and speed up the training loop. The actual test is a synthetic next token prediction task. Specifically, the model has to learn to count upward modulo the vocabulary size. It's a fairly simple deterministic task, sure, but it perfectly verifies if the architecture actually works on a fundamental level. We're closely monitoring the loss in accuracy to make absolutely sure all these complex optimizations, the sequence packing, the GQA, the ALiBi masking, are playing nice together and not disrupting the model's ability to learn. And the results? Totally definitive. Monitoring those metrics confirms absolute success. The loss curve drops smoothly, the accuracy climbs predictably. The complete memory-efficient transformer learns successfully end-to-end. We've officially proven that you can aggressively optimize the memory footprint of a model without breaking it. And keep in mind, what we just walked through isn't some academic toy. This exact combination of xFormers, packed sequences, GQA, and SWI-glue is literally the foundational bedrock for training today's massive, state-of-the-art large language models. So, that quadratic bottleneck? It's really not the insurmountable wall it used to be. You've now seen the exact blueprint to build incredibly efficient models from scratch, squeezing every last ounce of compute out of your GPU. The techniques are real, the toolkits are open source, and the path to scaling is wide open. The only question left is, armed with these optimizations, how far will you push this technology? And what massive datasets are you going to conquer next? Thanks for joining me on this explainer, and keep building.